Hi, everyone. Welcome to this example looking at equations of lines in R3. The example we have today is show that the given lines are parallel. And here we have two equations of lines for L1 and L2. Now, one thing we have to start off with is that if two lines are going to be parallel, they must have the same directional vector. When we look at them initially, they obviously do not, right? There's a different set of numbers. But another idea we want to keep in mind is that when we express a directional vector, we want to write it in lowest terms, meaning when we look at the directional vector for L1, I say I could take out a common factor of 2 here. So let's analyze this for a moment. So the directional vector for L1, let's call it M1. If I take out the 2 as a common factor, I'm left with 1, -1, -2. Now this would be the directional vector for L1 in lowest terms. Now, when we look at the directional vector for L1, and we look at the directional vector for L2, we see that they are the same, just the signs have been flipped, meaning, we have positive and 2 negatives, and here we have a negative and 2 positives. So they're in a ratio of -1 with each other. So therefore, I can now say that the directional vector of L1, which we call M1, is -2 times the directional vector for L2, which let's call M2, right? So if I do -2 times this vector, right, -2 times -1, +2, -2 times 1, -2, and -2 times 2, -4. So they are related. They are essentially the same vector, just, L1 chose to write the same directional vector as L2 with a factor, a scalar of -2. So they are the same directional vector. So since they are the same, we can now jump to this conclusion and say the lines must be at least parallel, if not coincident, which, as we recall, means the exact same line. So how can we tell which situation we have? Are they parallel, or are they, in a way, are they the same line just written with a different set of numbers? Well, one technique we can use is that we take a point from L2, let's say the starting point here, -2, 9, 10, and we see, is this point on L1? Well, how do we do that? We use the parametric equations of L1, meaning if the point -2, 9, 10 will be on L1, then there must be the same t from L1 that can be expressed to find -2, 9, 10, meaning I'm going to look at each component. So -2, so the point from L2, the x component, if this is going to be on L1, I must be able to find a t that satisfies this parametric equation, right? This is the parametric equation from the x components of L1, right? 0 plus 2t. And when I see, I get t equals to -1. Okay. So for the x component to work out, I would have to put t equals to -1 in L1 to get to, let's say, this, at least this x component. Well, let's keep analyzing the rest of the components. For the y component to work, 9, that has to satisfy the equation, the parametric equation of L1 for the y components, which is 7 minus 2t. And when we do this, we again find that t is equal to -1. Again, this is really good. Now we're going to hope that the third component works as well. If the third component is also -1, then yes, -2, 9, 10 is therefore on L1, and therefore these two lines are coincident. If not, they are only parallel. Well, let's take a look. So for the last component, the z's, 10, for this to be on L1, it would have to satisfy this parametric equation, right? 3 plus -4t, so 3 minus 4t. And when we rearrange this, we get that t is equal to -7, pardon me, over 4. And now, just because of this, since this is not -1, therefore, we can say that the point -2, 9, 10 is not on L1, and therefore, these two lines are not coincident. This is not just the same line written with a different set of numbers. They are, in fact, two different lines. And therefore, we can now say that the two lines are indeed parallel.